Hello and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about AC and DC, that is alternating current and direct current. And specifically, we're going to be discussing it in the context of a circuit containing a resistor or a series of combination of resistors, basically a load resistance. In future videos, we may look at what happens with capacitors, inductors, etc. So basically, our DC circuit, our DC source, we often just represent as a simple battery. We connect it across the resistor, and so we have a battery with some EMF. If it's an ideal battery, then this EMF will be basically the output voltage, and then you have a resistor which has some voltage drop, and the voltage drop, delta V, is the current times the resistance, or in other words, the current is the voltage drop per unit resistance, and is given by epsilon over R. Now with this, we also have the power, okay, and so the power, you'll recall, is I delta V, which is I squared times R. Now this is all basically for a DC or direct current output. DC output essentially means that we have, let's say, a current versus time and a voltage versus time for the element, and both of them are basically just flat horizontal lines. They're not really varying in time, they're not fluctuating. There may be like very small fluctuation, like less than 1% of, or 1% of this signal, for example. But we can treat them as constant. Now let's consider an AC source. AC source we typically represent in a circuit by this symbol. Sometimes we put a plus and a minus with it, but this is our power supply. Again, we're going to have it connected to a resistor, and then again, we basically use that the current as a function of time, I of t, is something like I naught times the sine of omega t. It's sinusoidal. So if we were to go and plot again the current and the delta V for this circuit, rather than plotting a horizontal line as we had before, we now basically will need to have a basically a plot that has both positive and negative values to it. And so, for example, my voltage drop across this capacitor may look like this, and at the same time my current through I said capacitor, through the resistor, excuse me, and for the current I may get a similar plot. Basically should have the same basic period, frequency, that kind of stuff, albeit it's going to have maybe different amplitudes simply because it's on a different scale. So both of these end up with the same frequency, same period, that kind of thing. Delta V is I times R, ends up looking like I naught R times sine omega t, and this right here would be like delta V naught, or the amplitude of the voltage signal. If we want to look at power, power again should look like I squared times R, but now this is the current. So now I have I naught squared times R times sine squared of omega t. And if I want to get, for example, the average power, how might I do that? Well, for that, you basically can go and recall what power is defined as. And this goes back to physics 1, but power is defined, or average power is energy or work per time. And so it's sort of like the rate at which work is done, or the rate at which energy is delivered. So power is rate at which, in this case, either work is done or energy is delivered. That's sort of like the long definition of it. Okay, so in order to get an average power, we basically need to figure out the energy. And to do that, you can recall also that energy is area, or work is area under power versus time graph. Okay, so we come back over here. This is our current, this is our voltage. Over here, we could have also maybe plotted power. So power. And the power basically would just be like these two graphs multiplied by each other, which I'm just going to represent by another line. Over here, same basic idea, except for that you have squares going on here. So basically, your power graph for this is going to look more or less like this. And then it tapers down to here, and then it comes back up, and it tapers down to here, comes back up, and it tapers down, etc. So essentially, you could think of this as, and correctly think of this as, a sine wave, but it's been shifted upward so that the bottom of the wave goes to 0, rather than being centered around 0. And that's because when you square everything, these numbers all become positive. Not only is it shifted upward, but it also has double the frequency of the period. So power has double, and therefore half the period of current or voltage. All right. Now, again, we've said that energy is area under this power graph. So again, if I draw the power graph over here, power versus time, I basically am looking at the area under a graph that looks like this. And so we might ask, like, how much area do you have to get in order to properly get an average power? And maybe the easiest answer is do one whole cycle. So this is actually a whole cycle of the power graph, but you could do like one whole cycle of the current graph. So maybe I should actually label that in a second color just for the variety. So this collectively is one cycle of current. The black part only, this part right here, this is one cycle of power. Either way, when you find this area, this gray will be the same as this black area, and so you're going for twice as much time, you're getting twice as much area. Either way, when you go to take this average, the power P will basically look like the total energy of a cycle. We could label that as a U, divided by the total period. And what we end up getting is, as it turns out, a value of 1/2 of the maximum current squared times the resistance. Okay, so that's our average power. So let's write that down again. Average power for the AC signal is 1/2 of the maximum current squared times resistance. The maximum power, for what it's worth, is just I0 squared times R. Okay, so this is an average, this is a maximum. Now, let's kind of like find what current is this equivalent to. So this average power should be equivalent to something like an average current squared times R. So we basically just said that 1/2 of the maximum current times R. Remember that I0 is maximum current. 1/2 of I0 squared R is equal to I average squared times R. And that means that I average is 1 over square root 2 I maximum. This is what's called root mean squared current. Sometimes this is abbreviated RMS or lowercase RMS. Okay, and so this is basically your average current for the cycle. The average voltage is found in very much the same way. Basically, your delta V average will be 1 over square root 2 of your delta V max. So that's your root mean squared voltage. Okay, and that's basically it for AC and DC through a resistor. Essentially, your signals are in phase with each other. So let's write these down. So the voltage and current have the same period and they're in phase. That just means that delta phi is 0 degrees or 0 pi. That means that peaks and troughs line up with each other. Okay, second point is that the power is still I squared R, but I might be variable. This also, for what it's worth, is delta V squared over R. Both of those have a sine squared term. Proportional to sine squared of omega t. This is both are proportional to sine of omega t. So power has twice the frequency, half the period as current. And then last but not least, you have the average values. RMS values are 1 over root 2 of maximum values. So that is equivalent to saying like IRMS, or in other words, I average, is 1 over square root 2 of the current max. This is for current and voltage. For power, the average power delivered is half of the maximum power delivered, and the frequency is double that of the current. Okay, as a quick example, in the US, the wall power outlets tend to deliver 120 volts at 60 hertz. Sometimes it's 115 or 110 volts, but we'll say 120 volts at 60 hertz of AC. We want the average current and power delivered to an appliance of resistance 240 ohm. The maximum current is the maximum voltage. This would be the maximum voltage divided by the resistance. So we're looking at 120 volts divided by 240. That gives us 0.5 amps, and then divide by root 2 to get 0.35 amps. For the power, basically what you're going to do is the square peak current divided by 2